consists of a nucleus, which is tiny. The metaphor that Rutherford himself used was it's like a fly in the center of the cathedral. And then orbiting this nucleus in, I should add, fairly blurry orbits are the electrons, which sort of fill out very sparsely the rest of the space. So that's our picture of these atoms. Subsequently, we learned that the nucleus is not itself fundamental. The nucleus contains smaller particles. They're particles that we call protons and neutrons. And in the 1970s, we learned that the protons and neutrons aren't fundamental either. So in the 1970s, we learned that inside each proton and neutron are three smaller particles that we call quarks. There are two different kinds of quarks. By the 1970s, I'm guessing physicists didn't have a classical Greek education, and they'd kind of run out of, classy names. So we call these quarks the up quark and the down quark. Okay, for no good reason. It's not like the up quark is higher than the down quark. It's not like it points up, and just no good reason at all. The up quark and the down quark. So the proton consists of two up quarks and a down quark, and the neutron consists of two down quarks and an up quark. Okay, this, as far as we know, are the fundamental building blocks of nature. We've never discovered anything smaller than the electron, and we've never discovered anything smaller than the quarks. So we have three particles of which everything we know is made. And it's worth stressing, that's kind of astonishing. It's we sort of take it for granted. We learn this in school, we don't really think about it deeply. Everything we see in the world, all the diversity in the natural world, you, me, everything around us, just the same three particles with slightly different rearrangements repeated over and over and over again. Okay, it's an amazing lesson to draw about how the world is put together. So that's what we have. We have an electron and two quarks. And these aren't the fundamental building blocks that the Greeks had thought about, and they're certainly not the fundamental building blocks that the Victorians had thought about. But the spirit of the issue really hasn't changed. The spirit is exactly what Demokritos said 2,500 years ago. It's that there are like Lego bricks from which everything in the world is constructed. These Lego bricks are particles, and the particles are the electron and two quarks. It's a very nice picture. It's a very comforting picture. It's the picture we teach kids at school. It's the picture we even teach our students in undergraduate university. And there's a problem with it. The problem is, it's a lie. It's a white lie. It's a white lie that we tell our children because, we don't want to expose them to the difficult and horrible truth too early on. It makes it easier to learn if you believe that these particles are the fundamental building blocks of the universe. But it's simply not true. The best theories that we have of physics do not have underlying them the quark particle and the two quark particle. And the electron particle and the two quark particles. In fact, the very best theories we have of physics don't rely on particles at all. The best theories we have tell us that the fundamental building blocks of nature are not particles, but something much more nebulous and abstract. The fundamental building blocks of nature are fluid-like substances which are spread throughout the entire universe and ripple in strange and interesting ways. Okay? That's the fundamental reality in which we live. These fluid-like substances we have a name for. We call them fields. So this is a picture of field. This isn't the kind of field that physicists have in mind. This is what you think a field is if you're a farmer. or if you're a normal person. If you're a physicist, you have a very different picture in your mind when you think about fields. And I'll tell you the general definition of a field, and then we'll go through some examples so that you get familiar with this. The physicist definition of a field is the following. It's something that, as I said, is spread everywhere throughout the universe. It's something that takes a particular value at every point in space, and what's more, that value can change in time. Okay, so the picture you have in your mind is a field, is a fluid, which ripples and sways throughout the universe. Now, it's not a new idea. It's not an idea that we've just come up with. It's an idea which dates back almost 200 years, and like so many other things in science, it's an idea which originated in this very room. Because, as I'm sure many of you are aware, this is the home of Michael Faraday. And Michael Faraday initiated this lecture series in 1825. He gave over 100 of these Friday evening discourses, and the vast majority of these were on his own discoveries on the experiments he did on electricity and magnetism. So he did many things in electricity and magnetism over many decades, and in doing so he built up an intuition for how electric and magnetic phenomena work. And the intuition is what we now call the electric and magnetic field. So what he envisaged was that threaded everywhere throughout space were these invisible objects called the electric and magnetic field. Now, we learn this in school. Again, it's something that we sort of take for granted because we learn it at an early age, and we don't sort of appreciate just how big of a radical step this idea of Faraday's is. I want to stress, it's one of the most revolutionary abstract ideas in the history of science, that these electric and magnetic fields exist. So let me just, you're supposed to do demonstrations in this, and I'm not just a theoretical physicist, I'm a very theoretical physicist. It's very hard for me to do any kind of experiment that's going to work, but I'm just going to show you something that you've all seen. They're magnets, okay? And we all played these games when we were kids or when we were in school. You take these magnets and you move them together, and as they...
In Greece there is a province called Magnesia. From beyond the time of Homer. The magnet is a Greek word and of course contains the essence of its nature. Meanwhile, let's take this look. It's wrong. Here we are.